Okay, doing the solutions to the cycle A/B intermolecular properties quiz, and because I'm in a good mood today, I got my video in here. Hello, everybody. Okay, here we go. Like always, this is going to be probably a pretty cruddy video, but better than nothing to see. Here we go. The first question. For the combustion of methane, so we know methane is CH4, and if we combust it, we're adding oxygen. Anytime you combust a hydrocarbon, you get CO2 and our good friend H2O. Going to put a 2 there and a 2 there to balance it. Okay. They want to know how many liters of carbon dioxide gas are produced when 2 moles of methane react. Okay. So the first thing we're going to have to do is convert 2 moles of methane to moles of CO2. So it's a 1-to-1. So that equals 2 moles of CO2. And because they want liters, we can't use the periodic table. And because it's a gas, we're going to use PV equals nRT. So if PV equals nRT, then V equals nRT over P. So we're going to put in 2 for N, 0.0821 for R. And for T, remember it's 0 plus 273, 0 degrees Celsius. You add 273 for Kelvin. And we're going to divide by the pressure in atmospheres. In that case, that's 1 atm. You're going to do all of that out, and your answer should be closest to 45 liters. For this problem, it's unbalanced. So I'm going to put a 2 here. Then I'm going to put a 3 here. But now I have 7 O's. So I have to put a 3.5 here and multiply everything by 2. So that's going to go up to 7. 4, 6. Okay. Now this is a limiting reactant problem starting with liters of oxygen. Okay. So it says you have 0.5 liters of C2H6 and you have 0.5 liters of O2, and they want to know what mass of water vapor. Okay. So what we have to do is first off use PV equals nRT to convert these to moles. And when you use PV equals nRT to convert those to moles, you'll use an equation that's N equals PV over RT. And for each of these, you will put in, and it's going to end up being the same amount, you would put in 1 atmosphere times volume, 0.5, divided by R, 0.0821, multiplied by T, which in this case again is going to be 273. And that's going to give you the same number for both of those. And that's going to be moles of C2H6, and that's going to be moles of O2. Then you're going to use the balance reaction to simply convert to grams of O2. And I believe that it's around 0.3 grams of O2. Let's take a look. Yeah, it is around 0.3 grams of O2. So again, whenever you have volume or atmospheres or something like that, use this equation for gases, PV equals nRT. In this case, we used it to get moles, and then we'd multiply by the mole ratio here. This one would be 6 divided by 2, and this one would be 6 divided by 7, and we'd multiply them again by 18 grams per mole for water, and end up with our answer. Question 2 about intermolecular forces. So what we have here is a bunch of elements, argon, krypton, and xenon. Okay, and it wants them to, we want to talk about the boiling points of them. So the first thing we need to understand about all of these is they're all nonpolar. They're all just elements or gases of different sizes. Now remember, as they get bigger, they can become more polarizable, okay, more lopsided, whereas this one, helium, is not going to be as lopsided. Okay. So since they're all nonpolar, the only IMF they have is London. So we're not talking about chemical reactivity. We're not talking about dipole-dipole. B and C are the same thing. Hydrogen bonding is a type of dipole-dipole. So their London dispersion forces increase, and they're increased by this thing called polarizability. So remember, dipole-dipole forces are strengthened by hydrogen bonding, whereas London dispersion forces are strengthened by polarizability. Basically, the bubbles become lopsided as they get bigger. So let's go through, and what I'm going to do here is I'm going to speak out these. I'm going to draw the Lewis structures, then I'm going to speak out the comparison statement for you. So the Lewis structure for OF2 looks like this. I'm going to be hell lazy and not put the lone pairs all on the F. And the Lewis structure for OCl2 looks like this. Okay. So both of these molecules are polar, meaning both of these molecules have London dispersion and dipole-dipole forces. So there's a tie. There's no hydrogen bonding. What's going to break the tie? Well, we must actually strengthen the London. And it turns out that the London is strengthened with OCl2 because Cl is bigger than F. So OCl2 is polar and exhibits strong polarizable London dispersion forces and dipole-dipole forces, whereas OF2 is polar and exhibits standard London dispersion forces and dipole-dipole forces. Thus, the forces acting between neighboring OCl2 molecules are stronger, yielding a higher boiling point and a lower vapor pressure. Let's go ahead and do this one. I said N is in the middle, so we have NH. Doesn't matter where you put the H's. There's a Cl. My Cl's suck. Ah! And here's this one, N, and now we just have one H. Okay, so little tricky in this one because you actually have some polarizability and hydrogen bonding forces going. Let's just say that the hydrogen bonding dipole-dipole force, since dipole-dipole is stronger than London, anytime you strengthen the dipole-dipole, it's always going to beat out strengthening the London in some cases. So I wouldn't necessarily give you one that's this confusing on the quiz, but let's talk about it. Polar. This is polar. Okay. So they both have London dispersion, dipole-dipole, and their dipole-dipoles are strengthened by hydrogen bonding. Here we have N connected to H, N connected to H. Here we have N connected to H. The potential of forming a hydrogen bond is there between neighboring particles because of the large dipole that's created between those two. So the dipole-dipole is strengthened more in NH2Cl because it can hydrogen bond more. It's got both of these strong dipoles, making it really sticky, if you will. So NH2Cl is a polar molecule and exhibits London dispersion, intermolecular forces, along with dipole-dipole forces and 2 hydrogen bonds, whereas NHCl2 is a polar molecule and exhibits London dispersion, intermolecular forces, and dipole-dipole forces with 1 hydrogen bond. Thus, the forces acting between neighboring NH2 and Cl molecules are greater, yielding a higher boiling point and a lower vapor pressure. Let's do this one out. You're going to get a WTF on this one. And watch out, this is linear, even though there's lone pairs. So this molecule ends up being non-polar, yielding only London dispersion intermolecular forces. Whereas this molecule here, and actually if we want, we can draw the resonance hybrids going on here, is polar. This is bent, exhibiting London dispersion and dipole intermolecular forces. Okay, so we don't need to talk about hydrogen bonding. We don't need to talk about polarizability. We don't need to talk about anything like that. Let's look at this here. So O3 is a polar molecule and exhibits London dispersion IMFs as well as dipole IMFs, whereas XeCl2 is a linear molecule exhibiting only London dispersion IMFs. Thus, the forces acting between neighboring O3 molecules is greater, yielding a higher boiling point and lower vapor pressure. Remember, dipole is always greater. Now, a lot of you guys are struggling with identifying whether or not something is polar. So let's take a look at each of these. If you draw it correct, regardless as to whether the dipole, in this case, is pulling towards chlorine, is moving in or out, if these arrows are opposing each other or colliding, they cancel. Okay. In this case, it's kind of tricky to see where the arrows are going, and this molecule is just very asymmetric. You can look at it that way. But if there were arrows, these molecules would not be colliding or being pulled apart from each other perfectly. So in this one, it's hard to draw the dipoles because they're all the same, but because it's bent, this molecule is asymmetric, and we are going to have a polarity to it. Sodium chloride is least soluble in which of the following? So we know that solubility follows the term like, dissolve like. Similar IMF forces dissolve in other similar IMF forces. So NaCl is so polar, okay, meaning that instead of being partially negative and partially positive, this electron was completely ripped off of sodium, yielding Na plus and Cl minus. So a molecule like this is going to be soluble in a polar molecule. Right? And we can look at it in terms of like water. We know that water looks like this. And the Na ion is going to get headbutted by the water, whereas the Cl ions are going to get slapped. Okay, just like we've been drawing them before. So you can think of ionic in terms of the like dissolve like rule as being very similar to polar. It's just a really, really exaggerated version of polar. So it's going to be least soluble than one that's non-polar. So that's polar, polar, polar. This actually H bonds, and so does this. So it's going to be really soluble in that. This guy right here is non-polar. Arrow, 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 arrow. These cancel, so it's non-polar. Below is the Lewis structure for xylene, the active component in a permanent Sharpie pen. So the first thing I want you to look at with xylene when you look at that is notice that it's non-polar. And if it's non-polar, that means that there's only London dispersion, intermolecular forces. Highly polarizable because this large benzene ring here. If you're interested in what that is, that's just a bunch of carbons connected like that with double bonds around like that, and then the hydrogen's coming up. So it's a bunch of T-planar carbons, and we call that a benzene ring. It's got strong resonance. Sometimes you'll actually even see it drawn like that with just a circle. So using the structure of xylene, justify why it is the active component in a permanent Sharpie pen. So I'm just going to speak this out. The assumption with a permanent versus non-permanent pen is that we are washing things with water. Water is polar, therefore only polar things will dissolve or get washed up by water. Because xylene is non-polar, it does not respond to water, thus it will not dissolve in it and will not be removed with the polar solvent water. Specifically, xylene exhibits only London dispersion intermolecular forces, which will not interact with the strong dipole-dipole intermolecular forces, those hydrogen bonds seen in water. Okay, 2. Design an experiment to separate the xylene from the other pigments in a Sharpie pen. So what we're going to do here is chromatography. I'm going to draw the setup right here. I'll put a little mark with a pen, and that's going to be the dot. That's the Sharpie dot, if you will. And then what you're going to put in it, not at the water, is a non-polar solvent. And this non-polar solvent could be like hexane. We use that a lot. And the hexane is gonna run up it, and after maybe like 3 minutes, what you're gonna see is that initial dot area kind of streaked up like this, separating out the pigments, okay? And this only works because we used a non-polar solvent. If you used a polar solvent, and it's really interesting if you do it, it goes right past that dot on the Sharpie pen. So step 1, place a dot of Sharpie on a filter paper, about 1/4 of the way up to filter paper. Fill a beaker with a non-polar solvent like hexane, layer that on the bottom above the dot, put the piece of filter paper in, wait for it to move up the filter paper via capillary action. Because both the dot and the Sharpie pen and the solvent are non-polar, the pigments will, especially xylene, dissolve in that nonpolar solvent and be separated from one another. Done. This challenge question, I'm going to give you a hint on this. The normal boiling point of Cl2 is 238. So we know that Cl2 is a nonpolar molecule and has only London dispersion forces. And the normal boiling point of HCl is 188. And we know that HCl is a polar molecule and has London dispersion and dipole-dipole. So that's a discrepancy. We would normally think the boiling point of this one here would be higher than this, but it's not. So they want you to account for the difference in these boiling points. And this is a little tricky. You're going to have to play the London dispersion tiebreaker, polarizability, against that dipole-dipole situation. And just justify your answer as best as you can. For that optional task, kind of silly, I want you to try and recreate that scene in the Lego movie. Now, you don't need to get redonkulous about it. All I need you to do in this case is get a Lego man and see if it works and set it up. And send me a YouTube video of it. I think that'd be really funny.